Okay, so this is the third video. Once again, my name is Clayton. And in this one, you can see at the top of the screen here, we're going to determine the stereochemical relationship between the following compounds, A, B, C, and D. So there are two strategies to do this. I'm going to walk through both of them. The first way that you can do this is by just determining the absolute configuration of each carbon and comparing them. I think this, in some cases, this way is easier. In some cases, the next way that I'm going to show you is easier. So it's kind of a case-by-case basis. I recommend knowing and understanding how to use both of these strategies. So the first thing I'm going to do is identify the like carbons, all the carbons that are the same. So here, this is I'm going to label this green one as the one that's bonded to the chlorine. So this carbon is the green one. There's my green one there. And okay, and then this back one, this is a Newman projection, is my green one in this case. Okay, so that's pretty good. And then I'll use orange for the other one. So there's my orange carbon, there's my orange carbon, and this just helps us keep track of all of our accounting. There's my orange one, it's the one in the front of our Newman projection. Okay, so now I'm just going to go through the process of getting the absolute configurations of each of these carbons. So I'm going to do this relatively quickly. I'm going to just try and kind of do this in real time. So feel free to pause it and work through this problem, and then just see if you get the same thing I do. And you can compare, and then we'll move on to the second strategy. So anyway, in this case, there's 1, 4, this is going to be 2, and that's 3. So that's clockwise. The green one is going to be S. In this case, we have 1, 2. Our hydrogen is to the back, and there's 3. So here we're going clockwise, hydrogen to the back. So this one is R. Here we have 1, once again 2. Once you do it once, it becomes a lot easier. I already know what the priorities are. So here I have clockwise. This is also going to be S though, because H is to the front. And let's do our last one. Oh, this one stinks. Okay, so the chlorine is on the back. So here's my chlorine. So there's 1. I know coming toward me is 2, there's 3, and H is right there. Okay, so for this one, I have my own little tool that I use. There's 1, let's see here. In this case, it looks like, no, it's like that. All right, yes, okay. So there's 1, 2, 3. 1, 2, 3. That's going to be R. So I got R for this one here. I use my fingers, so I assign like 1, 2, 3 or whatever, and then to the rear is my wrist. So this is the force substituent all the time, so that I can assign 1, 2, 3, and then when I look at it like this, I can just see is it clockwise or counterclockwise. The reason I use my hand is because I get to use my hand on a test. Nobody can take my hand from me. So that's why I use my hand to help me determine those things. But anyway, that's what I got there for that one. Let's see. Let's go to the yellow one now. 1, 2, 3, 4. So this is counterclockwise. H is to the front. Switch it around. It becomes R. There's 1, 2, 3. H is to the back. So that's R there. In this case, we have 1, 2, 3. So that's clockwise, but H is to the front, so that becomes S. And then in this one, I gotta do this again. So now, give me a second to orient. So this H, this becomes the top now. So now my wrist, I'm gonna put my wrist at the top, and I have going where it's the top. Oh no, I'm sorry. What am I looking at here? No, Wow, I saw that wrong on the last one. That's all right. Doesn't change anything. That's kind of funny though. So I'm looking actually at that, that, and that. So let me orient myself and then to the back. So to the top is the H. We have, so that's 1, that's 2, that's 3. 1, 2, 3. 1, 2, 3, counterclockwise. I got S on that one. All right, so hopefully you guys got the same thing. I am very confident that these are correct. And so now that we have our absolute configurations, super easy to compare them to each other. This is SR, so between A and B, and this is RR. Well, only one changed. That makes this a diastereomer. Now I'm going to look at A and C. SR, SS. Once again, this second one changed, okay? That's another diastereomer. So I'm just going to say DIA for diastereomer. Now let's look at A and D. SR, RS. Both chirocarbons flipped their configuration, or all the chirocarbons flipped their configuration. That makes this the mirror image. So SR to RS, that is going to be an enantiomer. Let's see here. BC. So compare RR to SS. That's an easy one. That's another enantiomer. And I already know by default both of these are going to be diastereomers, but let's explain why anyway. If we compare B and D, okay, only one changed, the other one remained the same. It's not a mirror image, must be a diastereomer. And then C to D, SS to RS, same thing. This first one changed, or flipped its configuration, so that is another diastereomer. All right, there we go. So that's strategy 1 for solving this problem. Let's jump to strategy number 2. Okay, so strategy 2 here involves converting everything to the same kind of formula. I think Fisher projections are the easiest to compare chirocarbons with. So what I'm going to do is convert B and D to Fisher projections, and then it's a lot easier to compare. So let's go through that process now. First thing I'm going to do here is simplify a little bit. I'm going to make this a CHO. Now I know this carbon isn't changing, but I do need to change this one. When I flip this, the chlorine is going to go to the back, and then there's my COOH. Now I need to flip this up and over. I'm going to rotate the carboxylic acid to the top because that's where these ones are, so I can compare them all equally. And then I'm going to flip it over so that the backbone appears to be flat. And so COOH, CHO. Wow, nicely done. It's like I've never used a pencil before. Okay, so now when I flip this, the bromine is going to be on the right, the chlorine will be on the left. All right, so there's that guy. Now this one, flipping or converting a Newman projection, what I want to do is put these, I want to put both of them at the top, or I'm sorry, at the bottom. So actually, and they're already very close to the bottom, which is really nice. So I'm going to go ahead and make that conversion. We could probably do this in our head, but I want you guys to see what I am looking at here. So in this case, we have H, we have CHO, COOH. In the front is our bromine, in the back is our chlorine. Now, what I'm going to do is flip this down, as if that's the right way to say that. I'm going to bring the bottom up like that. So the COOH in the back, I'm going to bring that to the top. So this is going to look like this. And in this case, we have both the bromine. The bromine is on the bottom one, and the chlorine, they're on the same side. All right, so there are our Fisher projections for these compounds. Now, if I just look at them, visually inspect them, A to B, so here's chlorine is on the right, now chlorine's on the left. So I know that configuration is changed, but this configuration has stayed the same. So these must be diastereomers. A to C, I have chlorine, bromine, both on the right. One of them is switched, diastereomer. Both of them on the right, both of them on the left for D. That's an enantiomer. Here, so if I compare B and C now, I have chlorine, bromine like that, chlorine on left, bromine on right, and here they're switched. Both of them are flipped. That's an enantiomer, right? So Fisher projections are really easy to visually inspect. We already know all the answers. I'm not going to go through every one. So again, both of these strategies are helpful in determining stereochemical relationships, and whichever one makes sense to use at any given time is definitely what you should be using, so make sure you know both of them. Thanks again. We're going to have one more video on stereochemistry after this one, and then we'll move to another topic. See ya.